Hello? It's oh geez, it's Thursday when we would be having class if it wasn't for the coronavirus. And I've prepared an example for you. It's kind of elaborate. So here's a system, differential equations. Is it Hamiltonian or gradient? It's going to be one of them. But Daffy Duck has wisdom for you. These dang things are never separable because if you look at the right-hand side, there's never any t's over there, but you're going to have a mix of x's and y's. So you're never going to have a dx dt equals x stuff and t stuff in these kind of problems. Sorry. So he's rightly cheesed off because wouldn't it be great if you had something halfway decent to do? So anyway, so here we go. I have the system written with factors and multiplied out so we can take derivatives easy. Everybody take a look at this real quick. Do you see a pattern there? Because I prepared this example to show you kind of a situational thing. If you're going to have a system that's going to play nice with either the Hamiltonian idea or the gradient idea, the system has been, it's almost as if it's been made ahead of time to work. Very situational. But on the other hand, when there's a structure running in the background and we don't know what that structure is, but we model the action that we see with differential equations, sometimes it turns up that the differential equations we get have these nice properties. So it isn't that, oh, these things only happen when somebody fixes it up ahead of time. It's more like a Hamiltonian or gradient happens when there's something running in the background and we just didn't know it. And this happens a lot when there's a mathematical property or principle running in the background and nobody knows because it just seems like, oh, everything's crazy. Look at these things that happen. I mean, imagine the fields that we've seen before, the direction fields that we've seen before with all these arrows all over the place. And people, that's all they see is the action of the rates of change. They don't see the actual structure running in the background. So this is what Hamiltonian and gradient give us a vision of. Okay, back to being serious students now. All right, so which is it? Well, you're supposed to check the partial of f with respect to x, the partial of f with respect to y. One of these things is going to match. I'm going to be extremely efficient and do f with respect to y. Let's take the derivative of this with respect to y, and notice we're going to get a 2x. We're going to get a minus 1. We're going to get a minus 2. That looks funny. That should be a 2x times e to the y. Sorry about these. Let me double check. Make sure I get these things right. 2x e to the y plus e to the y. That's right. All right, anyway, so 2x minus 1. We're doing the partial with respect to y, so this is minus 2x e to the y and plus e to the y. Now, if I did it right, g sub x should match. So the derivative of x squared is 2x. The derivative of minus x is minus 1. The derivative of negative x squared times e to the y with respect to x is minus 2x e to the y. And the derivative with respect to x of x e to the y is e to the y. So lo and behold, f sub y equals g sub x, so it is a gradient system. Now, how do we solve? Remember how to solve for gradient. There's going to be two integrals to do. You should have this on a little note page for yourself. Maybe your formula sheet, you modified it. So here's the integrals I got to do. I got to do the integral of, hang on, I got it over here. I got to do the integral of 2xy. I'm going to do this guy term by term. 2xy minus y minus 2x e to the y plus e to the y. And that has to be a dx. And there's going to be a plus a pure y piece. In case, the dx thing didn't turn up anything. So I'm going to get an x squared y minus xy minus x squared e to the y plus x e to the y plus, that little pure y adjuster. Then the other integral I got to do, oh, it's fitting. Very good. This is a lot. Look at all this stuff. All right, I got to do this guy, but with a dy on it. And you can see we're going to match. You can see it's going to match up pretty good. I don't think that we're going to have to worry about our adjusters because it's 4 terms each, and everybody's playing nice with what we got. I'm getting x squared y minus xy minus x squared e to the y and plus x e to the y. Plus a pure y piece, but the pure y piece, there isn't any because we have both of these things matching. All 4 terms match up. So we're done. This guy right here is my g of xy. Now, what knowledge does it give us? Well, it gives us a good amount of knowledge. We can kind of look back and see several interesting things. I'd like to factor it, because if I factor a y out of this thing, I get x squared minus x times y, minus, if I factor an e to the y out of this, a minus e to the y gives me x squared minus x. Notice how this minus sign distributes, giving me that plus x e to the y. Well, I've got x squared minus x written twice. So this g of xy is actually x squared minus x times the quantity y minus e to the y. And that's my big G. That's my function. Well, we can learn a lot from this because this can be plotted, and we can check the direction field that we would get from plotting it in 3D and looking at level curves, which I did. So this thing in 3D, let me erase here. This thing in 3D as a 3D plot looks like this. Give me a second. All right, here we go. Here's the x-axis. Here's the y-axis. So here's the level curves. This is not the surface. The surface looks like a saddle. It's a saddle, but it's a funny saddle. It's got an extra bulge around the y-axis. The curve looks like this. Sorry, not the curve, the level curve. The surface is doing this kind of thing. So along the y-axis, there's a little bit of a bulge, and this part right here, this little and then we have to have the solution curves are going to do this. They're going to ride perpendicular to this curve, so they're running in like this. It looks like we might have something going on over there. So let's find that little thing. We can actually find that spot. That spot ends up being the only equilibrium that we get in this system. So we can do, I'm going to now do nullclines with this thing. I've got enough time. Good. I've only gone 8 minutes. So I'm going to do nullclines using the factored form, because I've got the factored form up here. So if I have this thing equal to 0 and this thing equal to 0, there's only a few things that happen. X equals 1/2. And y never equals e to the y. For any y, you can graph y equals x and y equals e to the x. They completely miss each other. If you think about it, e to the y is always bigger than y. And they don't intersect ever. There's no place where there's a place where they're. So this factor is never 0. That's a big piece of information. And over here, I've got x squared minus x equals 0. That only works for x equals 1 and x equals 0. So I got constants out of there. And then I have 1 minus e to the y equals 0. That only happens for y equals 0. So if you look at it, I can't have x equal 1/2 and x equal 1. I can't have it. But I can have x equal 1/2 and y equals 0. That's the only equilibrium. And it's at 1/2, 0. All right. Now, there's a few more things. I'd love you to do these things yourself. But one of the things I can do to you is I can give you the direction field for this, have Maple print it up, stick it on the test. If you were to do it that way, it's actually a very boring direction field. Not much happens. But one of the things that does happen is we have an equilibrium at 1/2 0, which, if you remember the stuff I just drew, I had a bunch of solution curves all going to a point that I now know is 1/2 0. I got a bunch of solution curves coming at it. Now, I don't know if the solutions are running toward it or away from it unless I do what? Unless I do what? The Jacobian at 1/2 0. Then I can see what kind of system I've got. What's the local system at that point at 1/2 0? So let's do the Jacobian of 1/2 0. I already did it ahead of time. I urge you to take the derivatives. Probably want to take the derivatives from when it was multiplied out. You're going to do some partials. But what an interesting thing happens, the J, if you do J correctly, this piece and this piece, those two guys will be the same. Because one of them's F sub xy and the other one's G sub yx, and they turn out to be the same because we have a gradient. It's big G of xy, big G sub, this guy will be big G sub xy, and this guy will be big G sub yx. If you think about it, they have to match because mixed partial derivatives always match. That's running in the background. Anyway, so this thing, I urge you to do this Jacobian. I urge you to do it out, and you will get the following if you do it. -2, 0, 0, 1/4. I'm going to draw a smiley face because now I know what's going on with that equilibrium. Some solutions run away, some solutions run toward. So if I had the full direction field laid out, I'd know what's going on at the only equilibrium. I can tell what's going on no matter what kind of mishmash of arrows they give me. So this is the kind of thing you have to be able to do, you guys. It's going to be a test next week, next Thursday. If you want to take it early, get a hold of me by email. Send me any questions or comments you got. Thanks for tuning in.